All right. So you've been going over magnetic forces and fields. And so I'm going to write kind of, again, how I think of the basics. And we're using magnetic fields to talk about magnetic forces the same general way that we used electric fields to talk about electric forces. And I'll say this, magnetic fields and electric fields don't even have the same unit, so they aren't the same thing. So even if we draw an arrow, it's not the same kind of arrow. And you really, really have to pay attention to the difference between magnetic fields and electric fields. But just generally, if you remember, I said that electrical charges produce electric fields. For magnetic fields, say something a little bit different and try to emphasize the difference. And the difference is that things have to be moving. For instance, suppose I had a line of current into the screen here. Then the magnetic field lines circle around that. That's a lousy circle. So let me try again. Somehow it helps to go the other way. Magnetic fields circle around the motion of the charge. So to say that there's a current pointing into the screen means that either that positive charges are moving into the screen or that negative charges are moving out of the screen. Can mean either one. So you have the difference between positive and negative charges, of course. And then a right-hand rule tells you which way it circles. Because I've just drawn a circle, but it could be clockwise or counterclockwise. And the right-hand rule that I tend to use is thumb pointing along the direction of the current. So thumb pointing into the screen. If your thumb points into the screen, then your fingers are going to curl around clockwise. And so that's the direction that this magnetic field lines go around this thing. Of course, there's magnetic field lines throughout space. So there's a loop that I'm not going to draw the whole thing, but there's magnetic field lines everywhere, and they circle around everywhere. So anytime you're down below this current loop, this line of current right here into the screen, anytime you're down below it here on the screen, the magnetic field is pointing to the left. Anytime you're up above it, magnetic field is pointing to the right. If I want to draw a magnetic field vector for that current right there into the screen, and it's over here on the right, and I want to draw a vector, I need to draw a vector that points straight down. That current right there produces a magnetic field everywhere in space. If I'm over here on the right, that magnetic field vector points straight down. If I'm down below, it points to the left. So that's part one. And part two, so that's about moving charges. Moving charges produce a magnetic field. Magnetic forces come about when something feels that magnetic field. And other moving charges feel that magnetic field. In other words, there's a force on them because of that magnetic field. But they have to be moving. And I'm not going to sketch the right-hand rule, but we'll practice it a lot for the direction of the force. I will write the equation for the magnitude of the force vector. Once you've figured out the direction, the magnitude of the force vector is the charge that's moving, speed of the motion of the charge, and the strength of the magnetic field at wherever the charge is while it's moving. So the Q is the charge. V is the speed. And B is the magnetic field. So those two pieces, both of them have right-hand rules. Those two pieces and the idea that if there's a magnetic field produced by one current at a location, and there's a magnetic field produced by another current at the same location, the total magnetic field is the vector sum of those two parts. So when you need to get a total magnetic field, you need to add together vectors. That does not tell you how to draw magnetic field lines. Unfortunately, to really know the magnetic field lines for a complicated situation, you have to draw a whole bunch of magnetic field vectors across the whole space for the complicated situation, and then you have to connect the vectors to make magnetic field lines. It's not something you can just kind of instantly know. Except for the simple case where there's a straight line of current, then you instantly know the magnetic field lines, they're circles. All right, so the problems are mostly, the quiz problems I looked up are mostly just right-hand rule stuff, magnetic field, magnetic force, and things like that. And so let's just go through them. This particular quiz was set up in a funny way. You were given only these 8 directions to choose from for directions of magnetic field. So just because I suppose somebody had the symbol here, somebody made sure that all of the directions are one of those 8. And so this is all just about finding directions. So it's about using right-hand rules over and over and over. So let me just give you a couple of minutes for A, and then we'll do A, and then a couple of minutes for B, and then we'll do B, and then a little longer for C, I think, but first A. Give you a couple minutes. Talk about it, make your decisions. North, south, east, west, northeast, northwest, southeast, southwest. What would you put in that space there? All right, so it's basically a right-hand rule thing. So somebody want to tell me one of the, what did you think for A? Which of those compass directions would you pick for the direction of the force on this positively charged particle? The positively charged particle is moving toward the northeast. So northwest, I hear. Any other answers other than northwest? How many of you say northwest? Maybe I shouldn't ask for any other. How many say northwest? Yeah, it's northwest. So there are different ways of doing right-hand rule for this. The textbook, I think, talks about using velocity as your thumb, the magnetic field as your index finger, and your middle finger is the force. In the lectures, Professor Conway gives a similar kind of 3-direction where he uses the velocity again with the thumb He points all the fingers in the direction of the field, and then the direction of the force is the direction your palm would be pushing. Either of those should give you the same answer. So if you look at these things, velocity is northeast, so your thumb is pointing northeast. In standing this way, I've automatically put my fingers in the direction of the screen, and that means my palm is pushing northwest. And so the answer is northwest if that's a positively charged particle, because that's what this right-hand rule tells you is the direction of the force on a positively charged particle. That is positively charged, so the answer is northwest. How about B? I'll give you a minute to figure out B. Direction of the force on that lower particle, moving in a different direction, but in the same magnetic field. All right, so for B, anyone have a conclusion? Direction of the force? Southwest? Anyone have an answer other than southwest? How many of you agree with southwest? How many say it's southwest? Okay, I hope it is. No, I'm sure it is. Now you, at least for me, my hands are starting to get twisted up a little bit because I got to point my fingers into the screen. I want my thumb, with an outstretched palm, I want my thumb to point along the southeast direction. So my palm would point in the northeast direction. That would be the force on a particle that's charged positively. This one's charged negatively, so the force is in the opposite direction. So opposite to northeast is, in fact, southwest. Any questions about that one? All right, C is kind of a two-parter. They don't tell you the direction of the magnetic field. There's an electron that is moving to the right. It's directly above a line of current. So you have to think about the magnetic field, and then you have to think about the force, and you have to do that right. So you find the direction of the force due to that magnetic field. So go ahead and do those two steps. This one, the current that's in the wire produces the magnetic field, and the electron is the charge that feels that magnetic. This is a hint on the direction of the magnetic field. You could say, well, this current here is in a straight wire going to the right. If I look at that wire from the left side and look down the line of that wire from the left side here, so look down the wire, then the current's moving away from me. And that is this picture right here, current moving away from you. And so that's the direction the magnetic field circles around it if you're looking at it from the left side, looking down the current moving away from you. And so up above it, you should be able to find the magnetic field from that picture that I've drawn and that magnetic field direction. Okay, so in this one you have to do two steps. Let me ask you and here are the two steps. Moving electric charges produce magnetic fields, other charges field those magnetic fields. Let me ask you for the first step first. What's the direction of the magnetic field produced by this current carrying wire? This current here, the direction of the magnetic field at the location of the electron, meaning above the wire. Is it one of those 8 compass points, or is it something else? Pardon me? Out of the page? Everybody okay with out of the page? Who doesn't think it's out of the page, first of all, I guess? It is out of the page. If your thumb points to the right along this current, your right thumb, then your fingers are going to curl around the wire so that up at the top, they're pointing out of the page, in front of the wire here, off the screen, in front of the screen, they're pointing downward. Below the wire, they're pointing into the page, and behind the wire, they're pointing upward. So that's what that right-hand rule should tell you about how the field circles around this wire. Same kind of thing as saying here, if you're looking at this wire from the right, this picture way up here on the left, looking down that wire, there's a magnetic field up here at the top, since it's circling clockwise. The magnetic field up here at the top is pointing to the right. And if you figure out what that means according to this picture down here, that's out of the screen. So magnetic field pointing out of the screen, velocity of the electron to the left, to the right. And so what's the direction of the force on the electron? What did you get for that? Somebody want to hazard a guess? Yeah. Up? Anyone think anything other than up? Or north? Since it's one of these, that is one of the compass points, and that's what you were asked to choose. So up the screen, or north is the kind of direction that you were supposed to choose. So again, right-hand rule, thumb points along the velocity. Now I can face you, and I don't have to crank my hand around too much. Thumb points to your right. If my fingers point out of the screen, then my palm is facing downward or south, but the electron is negatively charged, so the force is in the opposite direction on it, so the force is up. Any questions about that one? Let's keep going. Now there's a same wire, I guess, a similar wire at least. Current to the right, a proton down below it, direction of the force on the proton. All right, so let me get a show of hands from everyone now. Where shall we start? Let's start with north. Let's start with north and go around clockwise. So this is for D. Direction of the force on the proton, the magnetic force on the proton in this situation. How many say it's north? Raise your hand so I can see it. I just want to know how many are. Okay. How many say it's northeast? East. Southeast. Can't tell if you're raising your hands or not. South? Southwest? West? Northwest? All right, the dominant answer is north, and a little bit of south also out there. So this one, if you're, again, the velocity is to the right. So your thumb can point to the right when your thumb is outstretched. So your thumb is held 90 degrees with respect to your fingers. The thumb is to the right. The magnetic field is into the board. We talked about that for the last problem, so I'm just going to say that. When you're down below, the magnetic field is into the board. Your thumb is to the right. Your palm is then pointing upward. And that's the force on a positive charge, and a proton is a positive charge. So north is what they were looking for there. So I said something. I said thumb perpendicular to the fingers. Now your thumb is velocity, and your fingers are magnetic field. In Professor Conway's way of talking about this, is the magnetic field necessarily always perpendicular to the velocity? Well, the short answer is no, it is not. And so you can, if the velocity is like this and the magnetic field is like that, then your, oh, can I even draw this? Then your fingers are like this, and your thumb isn't at 90 degrees, it's at some other, whoops, need more fingers in this, don't you? Your thumb isn't at 90 degrees, it's at some other angle, but there still is a force in the direction of your palm. Your palm is still giving you the direction of the force. Which reminds me that there can be an angle theta between the velocity vector and the magnetic field, and I totally forgot to put that into this equation because that is an important part of the situation. For instance, what if the velocity was in the same direction as the magnetic field? What would theta be? If they were the same direction, theta would be 0. What's the sign of 0? 0. There is no magnetic force on a moving charge if it happens to be moving along the magnetic field. It has to be moving in some direction, not along the magnetic field and not opposite to the magnetic field. Perpendicular, that's fine. So are there other directions that are not perpendicular but also not along the field. Those will give you forces. And the magnitude of the force is going to depend on this angle theta. Force going to 0 as theta goes to 0. I don't think that comes up in this quiz. I don't know if it comes up anywhere on the quizzes that I gave you, but I'll try to bring something next time where it does. All right, this was all part of one quiz. So since I put it on two things, I've messed it up a little bit. But let me go back and show you. Well, question C had the same wire to the right, parallel to the wire that's to the right in question D. So E is about the direction of the force exerted by the wire shown in C. C was up here. C was a wire up here with its current to the right. The force on wire D by wire C, if wire C is actually up here and has a current to the right. So that's question E for you. Again, it's a two-parter. Requires both right-hand rules. By the way, current you can think of as being a bunch of positive charges moving with the velocity in the direction of the current. It's either that or they're negative charges moving the other way, but negative charges moving the other way are going to give you the same answer. You can check this actually. Negative charges moving the other way should give you the same answer for the force. Negative charges moving to the left as positive charges moving to the right to make up that current that goes to the right through the wire. So force by the wire in C, which was above the wire in A, north of it, in other words. The force by that wire in C on the wire in D. So these would be two parallel wires with their currents in the same direction. In other words, both the currents were to the right. The wires were both horizontal on the page. So, two steps. Number one, moving charges produce a magnetic field. If wire number C is going to put a force on the wire in D here, in this question D, then it needs to produce a magnetic field at the location of the wire in D. So the wire in C was up here, it was up above, it was a wire pointing to with the current moving to the right. So what's the direction, what's the right-hand rule tell you about the direction of the magnetic field by the wire in C down here at the wire in D? Into the board? It's basically down below. We've already decided that down below for that kind of current is a magnetic field into the board. So wire D feels a magnetic field into the board produced by the wire up above it. And your right-hand rule tells you the force on this wire is what direction? Point, name something, point upward. Yeah, it's the north direction. Again, your right-hand rule, your thumb pointing in the direction of the current, because that's the direction positive charges are moving. Your fingers pointing into the screen, because into the screen is the direction of the magnetic field by this wire up above. And when you do that, your thumb pointing to the right and your fingers into the screen, you find that your palm is pushing upward, and so the force on these moving positive charges moving to the right, this current, in other words, is upward to the north direction. Any questions about that one? This next one is about the total magnetic field at point E and the total magnetic field at point F. And these are meant to be a little weirdly off-centered here, but this is meant to be a current, I think it says this. Yeah. Current I pointing into the paper. So on the left here is a current pointing along a wire pointing into the screen. And on the right is a current in a wire pointing out of the screen. So each of those produces a magnetic field everywhere. And your job is to find the direction of the magnetic field at point E, total magnetic field, and the direction of the total magnetic field at point F. And these are equal but opposite currents. I'll give you a couple minutes to straighten that out and think about an explanation. I don't think that this quiz asked for any explanations. I think all it did was ask for answers. By the way, this is still all part of the same quiz. So it's, right-hand rule, right-hand rule, right-hand rule, right-hand rule, right-hand rule. This particular quiz. Of course, this wire going in here, we've already drawn the magnetic fields. They circle around clockwise. Which tells you something about what the magnetic field direction at point E or point F from that wire, the wire on the left. So let's just go through this one. Direction at point E, The wire on the left produces a magnetic field. What's the direction of that magnetic field? Up, north. I'm just going to draw the picture. B by the current that goes into the screen. The wire on the right produces a magnetic field there also. Each of them produce a magnetic field vector everywhere. What's the direction of that? Down. And if I'm going to add them together, I'm going to have to figure out the difference between the sizes. Well, it turns out it drops off as 1 over the distance. So the point E is twice as far away from the line, even though I haven't drawn it correctly here. Point E is twice as far away. So what does that tell you about the magnetic field magnitude? Turns out it's half as much, half as big. And so the total is going to be up. On the other side, point F, what's the direction of the magnetic field due to the wire on the left? The wire on the left, the one that goes into the screen, up or down? Down. Half as big, so I'm going to write down B by that wire with the cross through it, the wire on the left. Direction of the magnetic field by the wire on the right? Up, north. And it's closer, so in fact it's half the distance, so it's twice as big. And so both of them are pointing up. The net field points up for both of them. North, in other words. Hope that's what you got. Since I didn't ask you for that. Any questions about that? All right, a short one, and then I'll go back to a longer quiz. I don't know where I got this problem, but an electron is placed at rest at a position near a magnet, as shown below. In which direction will the electron move? So I'll give you a minute or two to talk about it. Which direction will the electron move when you let go? And then think about an explanation, because everything needs an explanation. The explanation is what counts. The answer doesn't count. I'll tell you why in a second. Okay, so somebody want to tell me what they think? What direction does the electron move? Anyone want to tell me what they think? Yeah?
So I thought that the electric field lines usually move from north to south in the loop. But since it's an electron, it will go the opposite way of the magnetic field line.
Oh, I was going to say, you said electric field lines at first. So I was trying to, okay. So, okay, so what were you thinking was the direction of the magnetic field at that point?
It was from north to south.
So the magnetic field, magnetic field lines, they actually go, when you're outside, they go from north around to the south. When you're inside the magnet, they actually connect up in the other direction. But yeah, from north around to the south. And so what's the direction of the magnetic field of an electron that's just sitting there? Points to the right due to that south pole. So how do you determine the direction of the force? Right-hand rule, yeah. It's not going to move because its velocity is 0. So this is 0, the speed is 0. And so that would say the force is 0 because the speed is 0. Anyone disagree with that one? Because that is what I wanted you to think. That electron is not moving. Number 2 here, other moving charges. Wow, I can't spell magnetic, can I? Come on, you erase. Other moving charges produce or feel a magnetic field. The electron is not moving. It can't feel that magnetic field. Now, when I said the explanation was what I wanted, rather than an answer, the answer is that the electron doesn't move because there's no magnetic force, because the speed is 0. So the explanation is because the speed is 0, there's no force on it, so when you release it, it doesn't move. On the other hand, if you're tricky, or you're thinking about things really carefully, you know that this electron is... So I wanted everyone to say that it doesn't move because there's no magnetic force on it. And I don't think anyone at all made the argument that I'm going to make right now, which is this electron is negatively charged. So whatever this magnet is made out of, forget about north and south. This magnet, everything has positive and negative charges in it. Everything's made out of protons and electrons. That electron is going to slightly push some negative charge the other way and draw some positive charge toward it. And so this thing will, the electron actually will probably, if you just set it there, will probably be attracted to the magnet, not because of a magnetic field, but because of an electric field. I don't think, I remember this question, and I don't think anyone gave me that answer. Because it was the quiz on magnetic fields, so we weren't supposed to think about electric fields, I guess. A lot of people said, well, there's no force, so it doesn't move, and that's fine. But if you're being tricky, you could take it farther and say there's no magnetic force, but it does polarize the materials a tiny bit, and so there is an electric force. And you would be right. Any questions on that one? You need a moving charge to feel a magnetic field. So electron microscopes are filled with moving charges. In fact, electron microscopes don't use a beam of light. They use a beam of electrons. They produce a bunch of electrons. They focus the electrons. They do all sorts of stuff. So this is a little bit about, this isn't realistic, but it's a little bit about how you might focus a beam of electrons. We're going to make a converging lens for a beam of electrons, at least in this picture right here. So the picture shows the left to right paths of 3 electrons in an electron beam, and we want to go through a magnetic field that causes it to converge. So those 3 are going to converge onto each other, and there's going to be a focal point. Magnetic field at the top of the beam bends it down. There's a different magnetic field at the bottom. What's the direction of the magnetic field up above? Up above the beam. So the direction of the magnetic field that the electron up above the center of the beam feels, so that it bends downward. So that's the first question. We can talk about it a little bit. What's the magnetic field look like that bends an electron downward? So this is just the same kind of force problem with the right-hand rule, but it gives you something different. It doesn't give you the velocity. It tells you something about the force. What's the direction of the force on the electrons if I want to bend them downward? Better be downward. Electron's going along horizontally and I'm going to bend it downward. I better put a force on it downward. Physics 7b, the change in the electron momentum should be in the direction of the force. Momentum changes downward, so the force has to be downward. And here you have to figure out the direction of the magnetic field. So, what do you think? This way? Somebody pointing this way, out of the page. Is out of the page? How many say out of the page? How common is that answer? How many say into the page? Slightly more common, but equally, I don't know, both things possible. So the problem with the right-hand rules is for positive charges. All right, so how are we going to use this? There's a lot of ways through this. One way, if electrons were bent downward, what direction would protons be bent? Upward. If we had, or positrons. If we had something positively charged moving to the right, it would be bent upward. And so if you want to use your right-hand rule, you can just think about putting an upward force. Because an upward force on positive charges is a downward force on the negative charges. And so if your thumb points to the right, because it's positive charge moving to the right, you want your palm to point upward because positive charge would be pushed upward, and you find out that your fingers are pointing into the page. Into the page produces an upward force on positive charge according to the right-hand rule, and that means it produces a downward force on negative charge, and that's what you want. So into the page was what we were looking for here. Suppose the magnetic field discussed. Any questions on that one? Maybe I should. So up above, the magnetic field should be into the page. Down below, magnetic field should be out of the page. So you need to produce a weird kind of magnetic field to focus an electron beam. It's not a simple thing to do. You need the magnetic field in some way to circle around the beam. And you know how to produce something that circles around? Well, you just run a wire down the center. But you can't run a wire down the center of your beam or your beam's not going to be there. So producing that magnetic field is not a trivial thing to do in an electron microscope. You need a funny configuration of magnets to get a magnetic field that focuses. And I think what they do, I'm not sure exactly what they do, I think what they do is they focus in one direction and then they put on another beam that another magnet that focuses the other way. So that they end up with focus in two directions and a single focal point. But whatever they're doing, they need an electron beam and they need magnets to act as lenses. And so do you, if you use an electron microscope. Suppose the magnetic field discussed in part A was produced by a straight wire at point 1. So a wire right here at point 1 above the electron beam. What direction should the field be? So we remember what we wanted for this was a field into the page right here up at the top. And so what direction, if there's a wire that's going left and right, all possibilities for the wire. What direction should the current through the wire be to produce a magnetic field that you got? So produce a there's a wire at point 1. What direction should the current be to produce a magnetic field right here at the top of the beam that points into the page? All right, we got to hurry here. So anyone have an answer for that? To the right? So up here, if you have a current to the right, that'll be magnetic field out of the page up at the top and into the page at the bottom, circling around like that. So yeah, that should be to the right.